Okay, we're back here looking more into these polar curves. So we recently learned how to plot, sketch a polar curve by hand. And for the next couple of lessons, we're going to look into how we can describe the curve of a polar equation. And one of the ways that we can describe a curve is by looking at the symmetry involved. Many of these polar curves are going to have a symmetry of some sort. So just reminding you of the vocabulary here, we no longer have an x-axis, we no longer have a y-axis, we no longer have an origin. Those three terms are used in the rectangular system. Here we have polar axis, we have the line pi divided by 2, which is the vertical axis, and then we have the pole, which is what we used to consider the origin. So just understanding the terminology, let's see what we have here. So the first two ways that a curve can be symmetric. The first is with respect to the polar axis. So relating this back to rectangular, this would be saying something's symmetric along the x-axis. Here we're saying something symmetric along the y-axis. Let's use this terminology. So something symmetric along the polar axis, that means just along this axis, it's symmetric. So to test this, we replace the theta in the equation with negative theta, simplify and see if we get an equivalent equation, meaning simplify and see if we get the original equation, what we started with. Something to note here, it's going to be really good for us, save a lot of time, is if the equation only involves cosine, whether it be one cosine term or multiple cosine terms, it will be symmetric to the polar axis if it only has cosine terms. So looking at the symmetric with respect to the line theta equals pi over 2, this vertical line, so we can see how it's symmetric there. Now here to test this is we tested to see if replacing theta in the equation, we replace it with pi minus theta to see if it yields an equivalent equation. So similar process, but the reason why we use pi minus theta is because thinking of the angle that we could represent this point with, if it's symmetric, in fact, relating it to theta, we would say, oh, it's pi minus theta, 180 minus the degree value. So we're going to see a couple of these. Just here's something you could use to remember. If I want to look symmetry over the polar axis, okay, point in the first quadrant will go into the fourth quadrant. So what would help you here, first quadrant to fourth quadrant, okay, negative theta. Fourth quadrant, negative theta. So if I'm going from the first quadrant, polar respect to this pi over 2, first quadrant, we'll go to the second quadrant. Okay, so you're thinking here, okay, I want second quadrant, so that's pi minus theta. All right? I'll address that again at the end. So just like how cosine would yield symmetry to the polar axis, if your equation only has sine, it will be symmetric to this line, pi over 2. Okay, so we have the two ways of testing this. Let's look at an example to test this out. So test for symmetry. We want to see, is this equation r equals 3 plus 2 cosine theta, is it symmetric to the polar axis or to the line theta equals pi over 2? So let's test this. Let's test first for the polar axis. Let's see what we get. So we replace theta with negative theta. Okay? One great thing about cosine is we know cosine is even. Why that's good for us is because cosine of some negative angle measure is equivalent to cosine of the positive angle measure. So what we can do here is really rewrite this as if that negative theta was not there. And there we go. Yes, we got an equivalent relation. Yes, it is symmetric to the polar axis. Okay, so let's test the next one. So imagine we want to test it to the line theta equals pi over 2. Okay, so looking at this, we replace theta we replace theta with pi minus theta, because that would take us to the second quadrant. Okay? Now, in this, we're going to have to use some of our identities we learned in previous lessons, like previous units, actually. So what we're using here is the difference identity for cosine. And I'll put a little link right at this point, so you can go back and revisit that if you need to. So the difference for cosine is cosine, cosine, sine, sine. So cosine pi, cosine theta. If I'm subtracting, in the identity it's opposite. And then sine, sine. All right, and then now it's just a matter of simplifying. I'll put a little note here. We did the difference identity. Okay, now we just simplify. R equals 3 plus 2. Let's see, cosine of pi is -1. Cosine, okay. Sine of pi is 0. We get 0. Simplifying that, I'm just going to do a couple steps here. So this would go away. It would become 3 minus 2 cosine theta. And that is not an equivalent equation. Okay, so that is not an equivalent equation. So what we can say here is we're not going to say it's not symmetric. It's just uncertain. Uncertain of this symmetry. And I'll explain why in a little bit. So we know for a fact that this curve is symmetric to the polar axis, and we're uncertain about the other symmetry with the line pi over 2. Moving on. The two ways of testing polar axis, and the line equals pi, theta equals pi over 2. Okay, so let's see what we have now. So now new type of symmetry. Symmetric with respect to, sorry guys, the table I'm using, this table is my son and daughter's table, where they, eat, where they draw, where they color, where they do all their activities, and where they just snack, and it is sticky. Very, very sticky. All right, so, yeah, here we go. Symmetric with respect to the pole. So thinking back to rectangular, this is symmetric to the origin. So thinking 180-degree rotation. This is the only symmetry that involves rotation mindset, like a rotation view. So with respect to the pole, to test this, if replacing theta with pi plus theta to see if it yields an equivalent relation. So before we had pi minus theta, because that took us to quadrant 2. So you're thinking, I'm in quadrant 1. Imagine I'm in quadrant 1 with respect to the pole. So that would be taken from quadrant 1 to quadrant 3. So to be in quadrant 3, I'm pi plus theta. So pi minus theta, quadrant 2, pi plus theta, quadrant 3, and negative theta is in quadrant 4. Just a couple of things to help you out here. And we see this ending note. If any of these symmetry tests fail, the graph of the curve can still show symmetries. It can still show the symmetry of what the test failed on when you're done. And the reason being is because how negative r and like here, I could get this to work if I had, well, let's see, negative r comma theta. If you think about that, negative r comma theta, negative r, that would land us here. In this system, because of the ability for one point to have multiple representations, these tests, even though they fail, it doesn't mean that it's not symmetric. So the graphs, looking at the graphs, we'll be able to see more into this. But let's end with this one. Actually, not end, let's continue on with this one. So looking at test for symmetry, this is an 8. R equals 8 over 1 plus sine theta. Let's test the symmetries. We have 3 tests we're doing in this problem. So let's go. Let's test for polar axis. That's where we replace theta with negative theta. Okay. There we go. negative theta. And if using our understanding of sine and cosine, where cosine's even, sine is odd. So sine of negative theta equals negative sine theta. Okay, so this, because it's an odd function. So that would say r equals 8, 1 minus sine theta. And that is not equivalent to what we had. So test failed. So it might be symmetric, it might not be, but the test here failed. And then let's test for the line theta equals pi over 2. Okay, so we think here 8 over 1 plus sine. So theta equals pi over 2, that's the second quadrant, so pi minus theta. Okay, I have a difference here, so we're using the sine difference identity. So that would be, what would that make it? 1 plus, okay, the sine identity is sine, cosine, cosine, sine. So sine of the first, cosine of the second. If I'm subtracting, we're subtracting cosine of the first, sine of the second. Okay. Notice I did the bottom before the top, so I knew exactly how long my fraction bar would be. We have that, and then moving on, simplifying at this point. Let's see. 1 plus sine of pi is 0. So 0 times cosine 0. And then cosine of pi is negative 1 times sine theta. Okay. So that would make it 8 over 1 negative addition plus sine theta. Hey, yes. So we can say this is symmetric to the line theta equals pi over 2. And maybe we could have already said at the very beginning, knowing that little short trick that I shared in green at the very beginning, how if a polar equation only is in terms of sine, if it only has sine, that it's symmetric with respect to this line theta equals pi over 2. We could have used that and save a lot of time, maybe. And lastly, let's test here the polar axis, or the pole. Okay, testing the pole. Now that's where we take theta and replace it with pi plus theta. Right up here, we replace theta with pi minus theta. And up top here, we replaced theta with negative theta. Just helping us out as we close up. All right, so this is going to take it really quick. And we say r equals 8 divided by 1 plus sine of pi plus theta. Okay, so doing this rather quickly, we get 1 plus, let's see, sine pi cosine theta plus cosine pi sine theta. Okay, I'm running out of room. Let's see, we're going to do some simplifying more verbally than writing it down. Okay, so we get 8 sine of pi is 0, so this whole term is going to be disappearing. Cosine of pi is negative 1, but there's nothing to cancel the negative 1, so we get 1 minus sine theta, which is not the equivalent. So this would say test failed. Test failed. So I have one more for us. We've had 2 examples so far. Let's end looking at this problem. So let's test for symmetry. So r squared equals 4 cosine of 2 theta. So 2 theta is within the cosine function. So looking at this problem, let's test this out. Test polar axis, where we replace theta with negative theta. So r squared equals 4 cosine of 2 times negative theta. That would be negative 2 theta, or that would just be 4 cosine of 2 theta. Again, knowing that cosine is an even function, we see that it does work. Okay, so I'm going to put check marks here, and then we'll summarize at the end. Let's test now the line theta equals pi over 2. Okay, so that's where we take theta and replace it with pi minus theta. So that's r squared equals 4 cosine of 2 times pi minus theta. Okay, so that's going to be equivalent to 4 cosine of 2 pi minus 2 theta. Okay, difference identity, that would be 4 cosine, cosine, sine, sine. So cosine 2 pi cosine 2 theta plus sine of 2 pi sine of 2 theta. All right, that would mean for us that we get cosine of 2 pi is 1, so we get cosine of 2 theta, and sine of 2 pi is 0, so this term is disregarded, and we get what we begin with. Fascinating. That one worked as well. Lastly, ending with testing the pole, where we replace theta with pi plus theta. Move this up some. There we go. So we have r squared equals 4 cosine of 2 pi plus theta. Okay, giving us 4 cosine of 2 pi plus 2 theta. Sum identity, so 4 cosine, cosine, sine, sine. Cosine of 2 pi cosine of 2 theta minus sine of 2 pi sine of 2 theta. Okay, and giving us, let's see, 4, okay, cosine of 2 pi is 1, so we should get cosine of 2 theta. And then sine of 2 pi is 0, so that term is disregarded, giving us, again, our initial equation. So what we can conclude with, this equation is symmetric in every way that we can test. So this equation, r squared equals 4 cosine of 2 theta, is symmetric about the polar axis, the line, helps if you can see what I'm writing, guys. My apologies. There we go. The line theta equals pi over 2, and the pole. Okay, so testing each of them, you'll learn eventually through examples, just little tricks and ways to quickly get through them. But you're going to be testing equations and testing to see how they're symmetric along these 3 different ways. So good luck as you go and continue practicing this, and I'll see you in the next lesson.